This is Computing Up, conversations about computation writ large, with Michael Littman and Dave Ackley. This episode was recorded October 13th, 2022.
So, Dave, I've been getting a lot of news messages about awards lately. The MacArthur Awards were just announced, which is very exciting.
That. Yeah.
And the Nobel Prizes came out just a little bit before that.
It's that season.
So it's been making me think a lot about awards and what things deserve awards. I actually got to be, I don't even know if I'm allowed to say this, but don't worry, it's just between us and the handful of people who listen. I got to be a nominator one year. Cool. And I nominated a couple people who were doing work that I found really inspiring, I thought was important and should be honored.
You mean for Nobel or MacArthur or
no, not for Nobel, because there's no Nobel in computing, right? We have
it would have to be a Turing Award.
And so Turing Awards are done by nomination, and I have been involved in doing some nominations there. But the MacArthurs are not done that way. The MacArthurs are like the committee just says these are the people we want to honor, and they get their names from they draw magical means, So I suggested two people, one of whom you know very well, another one who was a guest on our show, and they did. Neither of them got the award, and the McCarthy people never talked to me again. So
screw them.
But as far as the Turing Awards are concerned, I have been involved in doing some nominations for that, and one of the things that I think is pretty cool is that the committee there seems to like work that has some kind of theoretical beauty to it, but also has had a big impact on the way that people actually practice computing. And one of the topics that hasn't been honored yet, but I feel like is very much in that corner, is a thing called SLAM, simultaneous localization and mapping.
Right.
So do you know about this? Have you played with this before?
I've never actually implemented it myself, and that's my only actual standard for understanding
knowing something. That's
so
fair.
I don't really at that level, but I've read papers about it, and I love the hell out of it, and I used it in science fiction stories and
oh, nice.
Yeah.
Well, you should be very excited because our guest today is Andrew Davison. And Andrew is one of the world experts on exactly this topic. So I can't wait to hear more about it. And he's also an expert on a bunch of other things, and he's interested very broadly. And I think it's going to be a fun conversation. So Andy, thank you so much for being here.
Oh, fantastic to be here. Thanks a lot for inviting me.
Outstanding. So maybe start off telling us a little bit about your trajectory. Like, how did you get to be where you are now?
Sure. Yeah. So I did a degree in physics originally back in the 90s.
One of them. Okay.
Yeah.
It's a great field to leave.
I guess I was interested in doing research after that, but couldn't think of anything in physics that particularly motivated me to do a PhD. And I was in Oxford, and I heard that there was this robotics research group there, in the engineering department. I invited myself over to meet a few people, and then was accepted for a PhD by David Murray, who was leading what was called the Active Vision Lab. So they're all about moving cameras, real-time vision, and mostly what they were doing at that time was things like tracking. So you've got an active camera. So this means a camera on a pan tilt platform, basically, and it was a stereo one, and they could move things in front of it rapidly and track their motion across the room. And really the start of my project was they developed a smaller version of this robot head that could be placed on a mobile robot base. And more or less the idea was, what can we do with this?
So it's maybe worth pointing out that I think people who haven't thought a lot about computer vision and maybe have only thought about the fact that they have their own vision is that the field of computer vision, the huge lion's share of effort has gone into basically analyzing things that look like photographs, like things that have been staged by people or snapshots that have been taken by people and selected. But normally when we think about vision, like our own human vision, it's all about moving through the world. Like that's the main thing that we use vision for. And looking at photographs is something that you can learn to do over time, and you can get a lot of information out of it. But so much of it is grounded in the real world, and the field hadn't done that so much. And it sounds like you're talking
Well,
about that kind of vision, the vision that's
I
actually in the
am.
world.
I am, and I think really that's what computer vision started as. It was let's give robots eyes, and then a lot of computer vision over the last 20 years, especially, has diverted away from that. Now that there's all this data, just internet photo collections and everything that people are working from. But I think I and a few others have always remained interested in the true sort of embodied vision problem, and vision for robots. Robot vision is really what I would describe my main interest as. So we had this robot head on a mobile base, and there were some obvious things to do in the short term, which were kind of the continuation of the active vision that you would do with a fixed active head. So, for instance, get a robot to navigate around some obstacles by fixating them and using some steering law. But we quite quickly started to think, well, wouldn't it be more interesting if we could give this thing a persistent understanding of the space around it? So can it build a map of things that it can see? And so my PhD project was really what turned out to be one of the earliest working SLAM systems, and definitely one of the very first that used vision as the primary sense. And essentially we used this robot head to sequentially fixate points in the world. So it would identify automatically some interesting points in the world that could serve as landmarks. And then it would take a look at them, and then it would move and it would try and look at them again. It would gather a set of geometric observations. And then the question was, how do you put that all together into an actual map? And so it became SLAM, or it wasn't called that in those days. That kind of tag came later, but it soon became clear that you've got these two kind of coupled problems. So you're trying to build a map, but at the same time, you're trying to localize yourself with respect to that map. So either of those tasks taken separately is much easier. But if you've got to solve them both at the same time, initially it's surprising that it's possible, but it is, right. And it's basically a coupled estimation problem where every observation that you make of your relative position to some landmark in the scene gives you some information both about your position and about where the landmark is. And the key to really making it all work was put that into the right probabilistic framework such that it becomes an inference problem where every measurement, you interpret what that tells you about both the map and about your position.
Yeah, because so you need to be moving around in order to get different perspectives. Otherwise, if you're just sitting there, I guess moving the camera will cause these landmarks that you're talking about to move as well. So there's some of that. But it's quite inherent that you want to move to see things differently, to get things in front of you and behind each other. But then you have to say, okay, well, now where the hell am I? And now when you talk about landmarks, you're not talking about Eiffel Tower, Taj Mahal, something like that these things are seeing. This is really low level stuff, right?
Yeah. So these are essentially interest points. So pretty much the same thing.
Contrast, light and dark, edge, that kind of thing.
We would usually use a word like corners because, you can easily detect edges in an image, but if you then move a little bit and try and match that edge, there's always this ambiguity. So you can slide up and down the edge. But if the point that you've chosen is something like a corner of a piece of furniture, then that is really, it's locally unique. So essentially what you do is cut out a little bit of the image around that corner, save it as a template, and then that will match very well to itself, but will not match very well to anything else nearby. So that means that when your camera has moved a little bit, you can find that same point, and that's what gives you the correspondence for these landmarks.
So I would kind of imagine, is it the case that you have like this huge family of hypotheses about how, and you have to represent, well, maybe this is part of that, maybe this is in front of that and so forth? Or is there some kind of collapsed way to just kind of have one idea and have it magically get better?
That's super interesting. And I think for a long time, I really imagined it would be a very sort of multi-hypothesis problem. But it turns out that you can pretty much get away just with following one mode. And most of the algorithms that are successful for SLAM essentially, model the whole distribution as a joint Gaussian over the whole.
Right. But it's just one distribution of where I think the stuff is.
Pretty much. And the things that enable that are, so first of all, the way that we detect and match these landmarks has got better and better. So in my thesis work, I really just was cutting out image patches and doing correlation to try and match them. But then, increasingly people developed better ways of doing, description of these points. So things like SIFT is a really famous algorithm in computer vision.
I don't know what SIFT is.
So it's a way of taking an image patch and describing it with a certain set of vectors which are really quite unique and have also invariance properties. So if you see that same point again under different lighting conditions.
It's a mathematical transformation you apply to a patch, and you come up with some arrows or something that is like more unique, gets the important bits. Okay.
No, that's exactly right. So that
sort of turns images into something more like a barcode, right? So a barcode, you can read it from lots of different angles, and when you see the same barcode again, you've seen it again, right? And so, but the real world is not so kind, and SIFT features give you a way of approximating that.
But then also it's not just about matching individual landmarks. It's about, even with something like that, individual landmarks will still be ambiguous. But configurations, if you like, constellations of nearby landmarks turn out to be really unique. So there's lots of algorithms. So things like ransack has been used a lot in these kind of problems. So that's another algorithm which is about looking for consensus between, a geometric set of hypotheses of where these landmarks are. So if I think that this landmark, is one that I know about, then this other landmark should be at some position relative to that, and this other landmark should be at some other relative position. So it turns out that pretty much you can stamp out this kind of need for multi-hypotheses in a per image way. So in each, when you're running a modern version of these systems, in each new image, you might be searching for dozens or hundreds of these landmarks, and you will only accept the motion hypothesis for your camera where a whole load of those landmarks line up in the right relative positions, and that is, it's so unlikely that that's going to happen in the wrong place, and unless you're in some deliberately difficult environment.
That's what I was wondering. What if you up in an optical illusion, or what if you put the robot in one of those Ames rooms where everything is all skewed? What happens to it then? Does it go nuts?
It certainly might do, or even something like a really long corridor in an office where all the doors look the same. Perceptual aliasing. So in that case, pure vision alone will probably have a problem, but usually in most robot systems you have some other sensors that will help. So you might have wheel odometry or inertial sensing or something else which is giving you a different sort of information that you're feeding into the same estimation engine that can often be enough to resolve those kind of ambiguities.
I would imagine it would also be possible, though, that the interpretation from the vision might sort of head down a wrong path for a while, and it might be okay, and then get to something that's completely ridiculous, and there would have to be a big pop, a big move in the distribution. Does that
Absolutely,
sort of thing happen?
Yeah. Definitely, and I think most SLAM systems would work in a kind of multi-level way, where there's some sort of process and feature matching that works from frame to frame on the assumption that you're pretty much just riding this single mode. And there's another process running at a kind of slower rate, which is just sort of checking.
Have we gone crazy?
Yeah. So in SLAM in particular, you have this loop closure problem. So if you
ask about that.
Yeah. So this really arises if you're mapping a large space. So however good your local motion estimation is, you will get incremental drift in your position estimate. So, if a really well-designed system, that rate of drift might be really low, but there'll always be some drift. So as long as you're always exploring new places. You'll be drifting. So that means that, for instance, if you go round a big loop and come back to somewhere you've been before, your map might not join up. So you might be a meter or two off, and your just kind of normal tracking process will not be searching in the right places.
Those are like two separate doors or something, when really it's the same door.
You'll map it twice. So then there's usually a process going on in the background, which is looking at the map as a whole and trying to find, are there places that actually look really similar to each other that I don't currently think are the same place. And if it does identify those, so that's a loop closure detection, and then it launches off another process which basically puts some pins into the map that says, well, these two places are actually the same. And go around and
everything else has to relax to
you bend the rest of the map round essentially until it all meets up again.
So gently morph it. So, and this, that to me feels very human, biological, right? So I've definitely had the experience of wandering around and going, wait a second, that's a thing. And like I can feel the mental map just go click and like back into this new state. Like, those are in the same place now.
That's what I was going to say too. I had a specific story about that. When I was an undergraduate, I went to Tufts University, which is outside Boston, and I would go into Boston on the T and walk around and see things. And I got to know little areas, and I had known other areas when I was growing up, going to Fenway Park, seeing the Red Sox and whatnot. And one day I was walking around a street that I sort of knew, and I took a turn and I looked up and I saw the Coca-Cola sign, which is this huge neon sign that you can see from miles away in Boston, which made absolutely no sense where I was seeing it. My mental map could not do it because I'd seen that from the bleachers in Fenway Park, and now I'm seeing it from this random little street in Cambridge. And all of a sudden, I felt it, just like you said, Michael. My whole map going like that, and I figured out what actually had happened. I think after the fact was that in my brain, the Charles River was straight. But it actually wasn't. And so I had rotated around by navigating relative to this thing that I thought was straight. So, I guess I was running I was running the loop closure detection. And so that's a whole separate pile of code. That's not the SLAM code being used again. That's a whole other thing.
It's normally a bit different. So, in particular, there's the sort of main SLAM code. It's engineered to be fast and kind of, So for instance, the type of features that you use are probably simpler because they don't have to. You're generally matching features, from 1/30th of a second to the next, and you don't need a lot of kind of invariance.
6 months and 3 years,
And the amount of ambiguity that can build up in that short amount of time is small. So you do something kind of simple. And then the sort of features that you need to detect loop closures are something like SIFT is much more likely to be used there. Right. It's a more expensive type of feature, right. and it's more of a search-like procedure to say, which place am I in? It's almost more like an image retrieval problem, and that in fact was some of the first ways that it was successfully done in Visual SLAM was more or less as the robot's driving around, just every second, for instance, just take an image and save that into a big database to say I've got these sticks in the ground where I took these images, and then whenever you capture a new one, you say, does this image look really similar to any of my existing images in the database? And that would be the first thing to trigger a loop closure hypothesis.
So it's a beautiful idea. It's sort of amazing how well it works. And when we were talking before, you were saying that part of it is because we, at least in the simple case, we assume it's the robot that's moving and not the world. And that if you're in a very busy thing with lots of stuff moving around, then it's more challenging to do this localization, even if once you had it, you might be able to hold on to it.
So most SLAM algorithms have that assumption built into them that the world is, mostly static most of the time, and the camera is the only thing that's moving. And of course, that is a pretty good assumption in most settings. And even in settings where you might think there's a lot of motion, like a room with people walking around, or a street with cars. If you actually look at the image and you ask, what fraction of the pixels in this image are static,
much the same, yeah.
It's really quite high. And even,
well, couldn't you also just focus on the features that are static, right? So you're in, I don't know, Times Square in New York City, and the buildings aren't moving, but the cars and the people are. So just don't use those as features for matching, or at least not for loop closure features.
I mean, in early vision systems, we of course didn't have any semantic knowledge. We didn't know which features were on people or which ones were in buildings. So we were down to sort of statistical ways of just hypothesize that the points are static, and then keep looking for them where they should be if they are static, and if they're not, throw them away. Yeah. But there are definitely methods now where you're running a CNN which is giving you some semantic segmentation of the scene, and therefore only choose features on the parts of the scene that are probably static. That's something that can definitely help.
CNN, not being the cable news network, but
a
convolutional neural network. Okay. Right.
So I would think that anybody who's seen a robot in a movie would think this had been solved, I don't know, 20, 40 years ago. The fact that this wasn't really a thing until somewhat recently, what has that enabled? What does that now make possible that wasn't really possible before?
Yeah, lots of things. So it's been amazing for me to see from when this was a research thing in the 90s that just a few of us were starting to get work. Now it is really in a lot of different products. So one that I've been directly involved in is robot vacuum cleaners that do SLAM. So I've worked a lot with Dyson, the company in the UK that makes vacuum cleaners and other products.
They got that tall one, right?
Yeah.
They
suck. They suck so well.
They suck all over the place.
Yeah. They're famous for that.
And so they're doing some kind of great grandchild of SLAM algorithms in the robot.
Yes. So I first met them in probably 2004 when I had been working on. So after my PhD work, I had I worked for a couple of years in Japan, also on robotics, and then I came back to the UK to Oxford, and then later to Imperial. And what I was really focused on was, could I do this visual SLAM thing without all the complicated hardware of a robot and an active head and all of that kind of stuff? Because I had this vision that if you could make it work with the simplest hardware setup possible, which is a camera connected to a computer, then this is really, really general purpose technology, because you can put that camera on almost anything and build a map and track where that device is. So I worked on this algorithm called MonoSLAM, which was, how do you do SLAM with a single camera, which is...
Because you said it was originally stereo cameras or something in the very earliest stuff.
That's right. So in that work, we had stereo cameras. It was, on a robot base. It had wheel odometry. We knew that it was driving on a plane. So all those things made the algorithm easier. And we had to find ways to relax all of those things so we could cope with general 3D moving camera, running quite fast, so we would assume it might be, carried by a walking person or a robot that was moving quite fast. And
should I be picturing like a person holding a cell phone and walking around, kind of scanning? Okay.
So that was really the form of most of our experiments in the early days, was just wave a webcam around in a room and try and build a map of the features there. So I was in fact, demoing that system after I had built it. And then I met some researchers from Dyson who had been working actually already for several years on robot vacuum cleaners. So some robot vacuum cleaners like the early Roombas were already on the market then. But
right, and they famously, like, they made a big fuss about the fact that they didn't have to make maps.
Do any
No.
of that.
Right, they worked
just
so
bumped
hard.
around.
Exactly, they like perfect randomness for bumping around just the right way to cover it. That's what they would say.
Perfect randomness. There's a concept.
Just like tuned randomness.
And it's surprisingly effective. And if you just bounce around a room randomly, you will.
Right, you just can't watch them do their work because it's painful to watch. Not because of the bumping, but because it's like, no, you just
already did that
spot. Right, and so, but given in the fullness of time, it will actually cover the space, and you'll get a nice clean room.
But it's inefficient, so and there's no guarantees that you'll reach any particular place. Right. So Dyson wanted to do it better, and in particular, Dyson have quite high power vacuum units, which work very well, but they're not the kind of thing you want out there running for hours. You want to be out there,
get out, get done,
cover the floor in half an hour, and come back to charge up again. So that requires precise positioning. And given that you don't want to go around your room and put up barcodes or modify it in any way, some other robot vacuum cleaner companies had proposed. You have a little kind of base station thing that maybe you put on the coffee table, and it beams a pattern onto the ceiling in infrared that then a device on the camera on the robot can see. But if you don't want to do any of that, you basically have to do SLAM. You have to build your own map. And Dyson at the time were very forward looking, I think, in thinking that they could use vision to do this. I mean, this now sounds like quite a normal thing. A particular interesting point about the robot they were building is that it had an omnidirectional camera. So this is a camera with a 360 lens, basically, that gives it a full 360 view of the room. And that is a really good sensor for SLAM, because this map of landmarks that you're building can be seen, whatever the rotation of the robot, if you've got a 360 camera.
I see those 360 cameras, and it seems like they distort the image tremendously. Do you have to do extra work to incorporate that back into the algorithm?
So, yeah, you do. You have to understand that distortion. You have to calibrate it, but basically the projection function that says how does a pixel on the image relate to the geometry of the scene goes through that function. So it does make it a little more.
But then it's relatively fixed. It doesn't change that much. No, I see.
So robot vacuum cleaners is so in fact all the other companies now also do visual SLAM. So iRobot's latest robot vacuum cleaners also do visual SLAM. But then there's tons of other sorts of products. So another really well-known one is AR or VR headsets. So if you look at the latest headsets from Oculus, for instance, or HoloLens, when those products first came out, you had to buy some kind of external tracking station thing that you would put in the room that would use lasers or something to track their position. Now it's all done just based on inside-out looking cameras, which essentially do the very similar thing of building a map of point features in the scene.
So they know where the walls are, and they know where you are relative to the wall. So they can project things into the space
and
that
put it on
look
the
like
wall.
They're real.
Well, they may do that. So for augmented reality, you may do that. For virtual reality, where you're not seeing the outside world, all that you need to know is the position.
You just know the orientation and
it's
position
really just
of the
tracking
headset.
Which
you think could just happen through inertial sensors, right? Just like as you turn, things shift.
But they're not good enough.
But that's not as tight. Okay.
So inertial sensing is very good for measuring rotation. Even just for pure rotation, it will drift over time. So gyros give you a very good measurement of rotation rate. But unless they kind of have a long-term kind of influence of something else, they will eventually drift over time. So when you have a camera as well, and the best systems do inertial visual fusion, so that really is the best way to track something like head motion. They build a map of features, and then the combination of visual and inertial measurements allow you to track full 6 DoF orientation and position in a
That's
very
degree
kind
of freedom for
Six
those who don't
degrees
know
of
what
freedom.
DOF is.
Yeah, exactly.
I think DOF means to take things off. Spelled differently, though.
Yeah.
So if I didn't even realize this, but that means, so if I was wearing one of these VR things and I was in a completely artificial kingdom or whatever playing a game, if I happened to be doing that inside a room that had just completely featureless walls with no corners, it would actually get into trouble. It would be difficult for it.
Yes, I assume so. At least the current products.
So that they just need something that isn't moving, so that they can triangulate against.
That they can see is not moving, right? Exactly.
That they can see, Well, geez.
But then when you come to augmented reality, I guess that's where some of the the work we've done more recently becomes relevant. So if in augmented reality, you have a see-through display, so there's the same head tracking is still completely crucial, and it has to be super accurate. But then what you also want to be able to do is add. So the graphics that you see should relate to the things that are in the room. So you'd like to be able to put a virtual tag up on the wall, and then as you move around, it should stay looking there, as if it's stuck to the wall. Right. So in order to do that, your vision estimation system needs to reconstruct not just the motion of the device, but also as much information about the actual room and scene as you can. So that's really the later versions of SLAM have tried not just to build very sparse maps of points which enable localization, but also to increasingly map surfaces.
Better mapping, not just better localization, but better maps. Yeah, absolutely. Wow.
So we started to work in that area in around 2009, 2010, particularly with a student, Richard Newcomb, who was in my lab at the time. So some of the technology that had started to be available, consumer technology, was really crucial there. So GPUs, importantly, just gave us much more processing power that we could put into this real-time vision. And another interesting thing that came out around the time was commodity depth cameras, like the Kinect, which is a really kind of high quality device, which can give you detailed depth information for actually quite low cost hardware.
Right.
So the dense SLAM systems that we were working on would actually build full sort of surface reconstructions of rooms. And if you have that, then you have this possibility to then, do something like put virtual graphics up in the scene, which look like they're registered to fix things in the room.
And I guess from what little bits I've read that, there's really pretty tight timing requirements on those things so that the things don't drift and people don't get nauseous and all that, to get you can do as much as you can, but you got to get it done on time.
Yeah. So if you look at these sorts of devices are now being very seriously engineered, of course, in big companies like Meta. And the actual user requirements are incredibly tight, I believe. So in order for people not to get nauseous, I think it's all about reducing the latency. So the latency between when your head moves and when that new pose estimate is available, such that you can move the graphics in the right way, has to be really, really low. And cameras are now running at, I'm not sure, but probably up to about 100 hertz or something like that, with inertial fusion as well to keep the pose estimate really tight. And then also just the requirement on the kind of registration error. So if you want to move your head and that thing in the scene just looks like it's really stuck to the real world, that has to be down to kind of fractions of a pixel. So that puts really kind of tight bounds on how good your motion estimation is.
And so from 1990 something or other, your thesis, to 2022, unbelievable arc for the SLAM concept out into these actual products and so forth. So I looked at your website and stuff, and so there's this other concept, this spatial AI, that you see, I guess, as a generalization, or the destiny of SLAM. What's the difference? What's spatial AI about?
So spatial AI is a term I've been using recently, which I think describes what I've always actually been interested in, even though I've mostly been calling it SLAM. It's how can an artificial device with onboard sensing and compute in real time capture a representation of the world which enables it to do intelligent things. So that's the sort of simplest statement of it.
It's embodied AI,
yeah,
robotic AI.
So it's definitely, I'm thinking about robotics mostly when I use this term. It's what level of scene understanding does a robot need in order to do intelligent things? And something I strongly believe is that a system like that should build a representation of the scene around it. So you might call it a world model or some kind of representation which in my mind has to have, both geometric and semantic properties. So I'm now working on systems aiming at quite general sorts of robotics. So think, for instance, the goal might be to build a robot that could tidy up a kitchen or something like that. So if I think about what does the vision system need to do to enable a robot to do things like that, I think that you need to build a kind of persistent representation of a scene, which you can then essentially use to try and simulate possible actions. You can link also probably to previous learning work that you have done. But increasingly, I think we want to build a system which can build, something like an object level map of the world, which then allows an intelligent agent to reason about all the things that it could do there. So when I talk about spatial AI, in my mind, it's the continuation of this whole SLAM project, which started focused on localization. It increasingly became about capturing
better mapping, and eventually you need objects to have good maps.
Right.
Yeah. We've been through the steps of adding sort of semantic layers to these maps. So this is, of course, thanks very much to a lot of the work that's been coming from machine learning, which allows you to do things like have a neural network which will take in an image and predict the semantic category at every pixel. So we've built systems where you then fuse that information out into the 3D world and can then have 3D scenes labeled with semantic properties. And then also trying to then break those semantic maps down into object instances where you may then, some of those objects you may have quite good prior models for. So you may have CAD models, for instance, of all of the objects in the Amazon or IKEA catalogs that you may try and fit to this visual information. But then there's always going to be things that you don't have good prior models for. So, to what extent can you use some prior information to build a sort of partial model, or are there some objects that you just don't know what they are, and the best you can do is just some sort of bottom-up shape reconstruction, and then maybe that information will come to you later.
Well, and it seems to me that when I think about spatial AI, when I think about space, and I think about space a lot, that just knowing the shape of something actually tells you quite a bit. That because it says how big it is and whether it's going to be a threat to me and how it's moving. Even if I don't know what it is, there's still quite a bit of affordances or something that I can get just from blobby things. And if I can then have some mechanism that would allow me to graduate up to say, oh, I get it. It's a soda can. That means I can pop it and drink it, whatever it is. But to not have lost that lower level fundamental geometric shape cloud something or other, that seems like a important bridge that we haven't really crossed yet, or have we?
Yeah, I mean, there's so many different approaches out there at the moment. I
I
think
guess so.
this whole question of recognition and how that should happen is very much a subject of a lot of research at the
It's
moment. So
exactly, yeah.
so you can reconstruct your whole scene in 3D and then apply some kind of 3D recognition algorithm, which might take, object models and scan them across this 3D reconstruction and see where they fit. You can also optimize the parameters of those shape models sometimes, or you may take a much more view-based approach, which says that the recognition always happens, in the 2D image. And this is probably where you can take much more off the shelf a lot of the kind of deep learning work that's being done at the moment. So if you recognize things in 2D, then you can try and take those recognized instances and then propagate those out into the map. So yeah, as I say, there's a lot of different methods at the moment.
I mean, it seems like it's developing all very, very rapidly now, and that. I mean, I guess I remember, the first time I saw the computer vision stuff, putting boxes around things and saying people, teacup, car, and stuff like that. It was like, wow, that's unbelievable, how they do it. And then it's in the end, it seemed, wow, it's very brute force. It sort of separately learned what a profile of a person looked like and a full face of a person looked like and so forth. And then it just put the same label on them at the end. But I mean, those are the keys. Those are the indexes that we get from reality, and we have to try to figure out how to then lift that up. Oh, it's Dave. Oh, it's Andrew. Whatever it happens to be.
So it occurs to me that it's almost a parallel to the simultaneous localization and mapping idea, which is, that you want to understand the objects and you want to understand their categories. Like, what is that thing, and what are the things like that like? But the problem is that the acronym would have been simultaneous classification and modeling, or SCAM. And so you probably want to avoid that, which is probably why you started with the geometric stuff, because SLAM is such a cool name. Bam!
Well, but it could be categorization, localization, and modeling systems, clams, and everything works. Geez. The the good old fashioned AI with Lisp and symbol pointers and objects, and put the block on top of the block and make an arch, all that stuff, which was really big when I was younger, and then sort of fell into whatever. And now that the sensory level stuff, which I'm saying pixels and all of this thing, the deep learning, just go straight from the audio signals to, is this statement true? Just go straight from pixels to, is it the Taj Mahal? That kind of thing is making such great success that it seems like it's getting to be time again to say, okay, well, where are these objects going to come back in? What are they going to look like? And, lots of people have theories about them, and theories about what they might be, and about how they might be implemented in capsules or assemblies or whatever it happens to be. But I mean, that seems like that's really the main chance. I mean, that's really, if we could now take this sort of sensory level, pixel level, signal level stuff, and actually get a robust notion of symbols with pointers on top, that would kind of be amazing.
And there's a lot of work still to do there. But one of the things we've been investigating in our lab is, so even within a restricted set of assumptions about objects. So let's assume, for instance, that you're looking at a scene and you do have pretty good models of all of the objects that are present. I still think we're far from exploring all of the things that you can do in that situation. So think about robot manipulation. So that there's a lot of recent exciting work on manipulation coming based on reinforcement learning in particular. But a lot of the demos are quite simple, learn to pick objects up, but then you just drop them into another box or something.
Right.
Whereas if you actually have a good knowledge of the shape of an object, then you can look at a scene and you can actually estimate the identities and 3D positions in a lot of detail of all of the objects that are there. And then, for instance, you can pick up objects in the right way to then place them accurately. So some of the work we did was take a pile of objects. You have a robot arm which has a camera on the wrist. It observes the scene. It estimates the shape and position and identity of all of the objects, and then can actually plan to tidy up that pile and put all the objects away in the right place on a shelf, and even do things like that. If you see an object and you can grasp it, but you can't grasp it in the correct way that would allow you to place it where you want to, you drop the object in a certain way such that you can re-grasp it, and then you have the right grasp in order to place it. So yeah, I still think we can go a lot further, with certain strong assumptions, which then hopefully we would gradually relax as we learn more about more general ways to build object representations.
I mean, I wonder if there's so we have these large language models now that we just put so much data in. And I wonder if there's some related but different sort of large world model or large physical model about how things in 3D space and 6DoF and all that stuff seem to work, that we could create giant data sets or whatever it is and train giant things, which we could then, instead of having a special purpose thing for these particular blocks and then learning how to tidy those up, we would make it parasitic on one of these giant, large geometry models or something like that. People must be working on it. I don't know.
I think so. I think it's very hard to think of where that data set comes from. That could be self-supervised in the same way that you can do with the language models. So it's not something that I'm personally
because really it was the internet with all those cat pictures and all that stuff that made the large language models and the text to image and stuff really possible.
Yeah.
I don't know.
Well, one thing that occurs to me is that we've been talking about localization, but I think, Andy, in the story of your trajectory, you didn't get to your current location. Like, where are you now? Where do you work?
Where do I work? So I work at Imperial College now. So
in London.
In London.
Yeah, exactly. So I'm leading the Dyson Robotics Lab at Imperial, which is a lab working on vision and perception technologies for home robotics mainly. And then I also have some other projects that I work on.
And so the Dyson Lab stuff has things that are intended to inform products, or this is a little bit further into the future of research, or both?
It's long-term academic research, which, it will hopefully have a long-term influence on products, but we're not directly developing products. And there is a big internal robotics research team at Oxford, at Dyson, which is doing that. Yeah.
I see. That's great.
Yeah, it's very cool of them.
Well, Andrew, so you and I met on Twitter, and we were talking about crazy possible futures, and like I said, I made this science fiction story that Slam sort of featured in as an element of the story, and that's how we connected. But I really feel like sort of like fellow travelers in this systems oriented, bottom up, take the signal seriously sort of thing. And so it's been really fun to talk. I really enjoyed this.
Well, thanks very much. It's been great.
This was Computing Up. Thanks for listening.